Well, thank you very much to Satoshi and the other meeting organizers. It's actually a great joy to be here at this symposium for the first time. With Nakajima-sensei here, I've been co-organizing a meeting around the RIKEN Computational Chemistry and Materials team for some years, and at the back is also one of the co-organizers of this meeting that was very successful, Dr. William Dawson. But the timing of that meeting has precluded me attending here as well, and so I'm delighted that this time it all worked out. And so I'm going to actually talk about a couple of things. I'm going to actually introduce a major new initiative in New York State in AI, and then I'm going to actually go back to sort of my roots in HPC and talk about some of the programming tools that we've been developing with support from the Department of Energy and also the National Science Foundation, and that's a large team project. So starting off with a conversation about AI, which is of course front and center, not just in our minds, but in our pocketbooks quite literally. I want to talk about the Empire AI Consortium. And so here you have a picture that actually sort of captures the essence of this initiative. So right there in the middle is Governor Kathy Hochul of New York State. And in April, just last year, 2024, she announced an initiative that essentially amounts to a $500 million investment by the state in partnership with academic institutions across the state in AI for academic research in service of the public good. And you can see me hiding at the back. In the front, we have the president of the University of Buffalo, where this event was held. On the left, we have John King, the chancellor of the SUNY, State University of New York system. That's a system with 650,000 students and staff within it, so a huge system, second largest in the country, second to University of California. Next to him is Marilyn Simon. So she and her now past husband, Jim Simons, billionaires and big benefactors of basic research. So they operate, for instance, the Flatiron Institute in New York City, and also have generously invested in Stony Brook University, which is my home institution. And then on the right of the governor, we have Tom Secunda, another billionaire, one of the co-founders of Bloomberg Enterprises. He and the academic partners were really the genesis behind this initiative, basically realizing that there's a massive gap between what academic research can do in the space of AI and its applications, and translating that, of course, into benefit for the state, not just economic impact, but all of the workforce development and all of the other things that states need to be doing to maintain their competitive edge. And so he, in partnership with these institutions, went to the state and in very short order convinced the governor of the significance of this potential. And that was actually underscored in Satoshi's presentation this morning, where he documented the economic impact of Fugaku. That's just amazing. And that's something that we should all be aspiring to be able to report. Anyway, so the state has committed $25 million to the initiative. And let me just jump ahead here. Here is the list of consortium members. So presently there are 6 consortium members: CUNY, Columbia, Cornell, NYU, RPI, and SUNY. Associated with this project very intimately is the Flatiron Institute in New York City, and I'll come back to that in just a moment. So again, our mission is to serve the public good through performance of academic research. And closing that gap with industry is now easier said than done, right? I mean, so when we first started this conversation, AI resources in industry were already easily surpassing $1 billion. And we thought, well, $500 million is going to get us close. But now, of course, you've got industry talking about individual AI facilities, fully integrated, that are going to be costing up to $10 billion, right? So that really sets the scale for what we need to be trying to accomplish. So the state investment is supporting primarily capital equipment, and the partners are providing operating funds with an initial timeline of 10 years, but no one is thinking of this as a 10-year project. We've all got 20+ years in our mind. No one is really thinking of this as a $500 million project. We're all thinking 1 billion up by the time we aggregate all the various possible sources of money over this next decade. The board members are listed here. Basically, they're representing the institutions along with some key partners in New York State and some independent observers. The timeline I already mentioned, the announcement was really formalized in April 24. In January, actually 25, the governor just announced in her budget address her intention to provide another $90 million match for the project. And that's in part to facilitate the addition of new consortium members. So we're going to be growing. And basically, because operating costs don't grow linearly with the size of the system, a large part of the funds, both operating and capital, are just simply going to get folded into growing the size of the computing capability. Our first system, Alpha, that I'll talk about in a moment, is already operational at the University of Buffalo. And I actually just this morning, sitting here in this room, sent off the final PO to a company to purchase the beta system. So that's far from being officially announced yet. So this is really the first public news of this event. Also awarded this month was the contract for the conceptual design of the facility. So that will be eventually roughly a $50 million building with electrical infrastructure and so on, sitting up on the University of Buffalo campus. Buffalo is the hometown of the governor, so that's one reason to favor this location. But I'll come back to its key role in the sustainability plans of the project as well. This summer, this beta system is intended to be operational, and we're anticipating also the initiation of construction of the facility. And then if you look out a little over a year, the facility will start to become operational and we can start to install the next system. We're anticipating installing roughly 3 generations of the system over the sort of roughly 7 years of the project, in part so we can track latest technologies, in part anticipating price advantage by deferring some of these investments, and also just simply being aware of the pace of evolution of not just the computing technology, but the actual associated algorithms and software stacks, right? So what we should be doing 7 years from now is far from clear right now, and we've already heard that from Satoshi's presentation. So Alpha really is an eye-opening opportunity for me, coming from academic research, where money comes through onerous writing of grant proposals and so on. Alpha is really the result of a simple donation by Marilyn Simons to the project of a system that the Flatiron Institute was about to deploy, but she and Tom Secunda agreed that there'd be a tremendous return on investment and big benefit to the state by sharing the system freely with all of the universities in the consortium. So this is providing us with a compute platform well in advance of our anticipated first deployment. And you can see it contains roughly about 100 NVIDIA H100s. Actually, this is a good opportunity for me to talk briefly about beta. So beta, as I mentioned, is going to get deployed this summer, and we're presently anticipating it to be an NVIDIA DGX GB200 SuperPod with 288 GPUs in it, along with a significantly sized flash storage system and some component of general purpose HPC compute. I mentioned up in Buffalo, a strategic aspect of putting the machine there is its situation very close to Niagara Falls, and that gives us very inexpensive and also very sustainable and significant amounts of hydropower, and so we're going to be essentially powered by the cleanest source of energy that we can find. And of course, the system's going to be directly cooled, as all these technologies are these days. And already part of the University of Buffalo's campus master plan is to take the excess heat from our system and recycle that, capture that and recycle it, recirculating it into heating buildings and so on. So if you have any questions about Empire AI, most of you can already find me online. And otherwise, there's sort of our public communications email address. As you can tell, we're not even a year old yet, and we're moving very fast, and we're certainly looking for partners in this space. So now I'm going to switch topics. Okay, great. So looking around the room, I see a lot of colleagues from the Department of Energy. I was going to say old colleagues, but that would be, with the passage of time, have two meanings to it, right? Former colleagues and old colleagues. So a lot of this work really stems from collaborations that had their genesis when I was working alongside the DOE eXtreme-scale computing program at Oak Ridge National Lab and subsequently at Brookhaven National Lab, and have continued now that my main academic appointment is as director of the Institute for Advanced Computational Science at Stony Brook. And so here we have an initiative that we're executing in the spirit of co-design, basically asking the question, what do scientific applications need? What are the challenges that they're facing when looking at trying to take state-of-the-art science and associated algorithms and get them onto the really complicated hybrid, with strong NUMA characteristic systems that we're facing today. And so this project is really centered on that. It's centered around also the Parsec parallel runtime and task execution environment. And that was at the frontier of early success in dense linear algebra in using DAG-based execution models so that you could get very scalable and efficient scheduling on distributed multi-core and also hybrid computer systems. So the real genesis of this was a conversation between myself and George and Thomas here about the potential of doing that. And we're now several years down the road of trying to make that happen. In order to cue up this conversation, I'm going to talk a little bit about Madness, which is a computational framework that I've been developing with a community team for some years now. And it's a general purpose computing environment motivated initially by the needs of chemistry and physics, but with now fairly broad applications in multiple spaces. And a key motivation is that we want algorithms that are robust, meaning with guaranteed accuracy, fast, in multiple senses of the word, and also are easy to write. And of course, you put all of these words in a sentence and you start objecting to the feasibility of this, right? And Phil Colella articulated, I think, very clearly the idea of the semantic gap. Why are our equations a few pages long and our software stacks literally millions of lines, right? This is a recurring theme, managing complexity, right? Underlying what we do is a bunch of math, fast algorithms. We're essentially doing multi-resolution analysis. But if you know about the fast multipole method and the multi-grid method, we're essentially using a lot of the same math and tools that sit under that, but rephrased in a different context that focuses on a guaranteed accuracy and operators. This is the very highest level of composition that we have in the code. We can write small, real applications like this. This is a real program. And of real interest to chemists here is that this is now solving essentially a small, but still physically relevant problem with guaranteed accuracy and speed in a distributed memory parallel setting, right? We're not in a position where we can do this on a full-up science application. This is more of a proof of principle here, but this is sort of like where we're striving to get to. This is the math sitting under everything. We can just skip over that. That's not the topic today, except to say underneath all of this is essentially computation on trees, right? We essentially have a hierarchical representation of a discretization, typically in 3 or 6 dimensions, and trying to represent the state of multiple functions, each of those functions having their own independent, adaptive, and dynamically refined mesh. And it's dynamically refined because we get our speed in large part by not doing anything exactly right. So you want to compute only what you want, not just only numbers that you want, but only the bits and pieces of numbers that you want. Okay. And so that leads us to having irregular composition, and because of the physics of some of the problems we're looking at, we end up with very deep refinement of some of our trees. Madness now dates back some years, potentially decades. I don't want to start counting that far. And it's based on a runtime that was essentially implemented to serve its purposes, but that runtime is now long in the tooth, and I'm going to look at some of the underlying issues there to motivate where we're going with TTG. Task-based parallelism, as I've already mentioned, and to compose those tasks together, essentially to hide latency in either tasks that haven't yet executed, producing results needed for future tasks, or in other aspects of latency, such as I/O or communication that might be introduced. We use futures to hide that and pass the dependencies into the runtime system. There are various tools to allow distributed shared memory programming in various settings, and to also enable physicists to express their code and the scheduling of tasks and placement of data in the context of scientific elements of their application, rather than specifically naming processes and even threads and so on. Where we're focused here today is really on the task programming layer, and overall tasks have been really successful, right? I mean, I think we've, especially in the multi-core setting, have been really satisfied with those, even in distributed memory, and they especially serve well the needs of irregular applications. But I think as many people have learned already, there's also a dark side to tasks, right? So what we're doing inside Madness, composing tasks, connecting them with futures, is essentially manual continuation passing. If you don't have a compiler, then to do that for you, then you're manually decomposing. Every time something's going to block, you basically have to split things into 2 and pass that dependency between tasks. And so you very rapidly get to a point where you're making rather rigid decisions about granularity and decomposition, unless you're approaching this from a code generation perspective, right? And certainly we have some of those tools as well. It also makes your portability from CPU to GPU worse, really, because the code becomes harder to refactor. And then on top of that, this manual continuation passing, you often end up expressing nearly all of the DAG, all of the tasks in an entire DAG before execution can start. And so you can imagine that if you've got a traversal that has to go from the bottom all the way to the top of the tree and then come back down again in order to move some data around, you can potentially initiate and store some data structure associated with every node in a massive tree that might have trillions of nodes in it. And so this just becomes a tremendous resource issue, and it gets in the way of the ease of composition, right? So we kind of see how to address the level of composition in terms of the scientists, the science layer, but what we want to do now is address that middle layer where we want actually the underlying numerical piece of madness to be easier to write and have essentially this nirvana of portable performance. And of course, the solution to that is a more successful separation of concerns. The runtime needs to be more intelligent. You eventually need intelligent compilers, and we're not at that point yet. So there's multiple styles of task-based programming. As I mentioned, madness you can view as continuation-based programming. What the TTG that I'm going to introduce is, it's basically an abstract task graph, right? So it's basically you're programming now a generator. And so TTG, a template task graph, is the main product of this large collaboration. I already motivated that it came from the success in dense linear algebra in this style of composition. Here, for instance, in the bottom right, you've got a DAG, meaning the actual computation that is executed, and that horrible sort of like IBM JCL-like stuff, if anyone's old enough to remember that, otherwise maybe Perl-like stuff, is the DSL that they use to specify these dense linear algebra applications in terms of a generator, independent of the size of the problem, that when executed will generate a graph like that on the bottom, but potentially many times larger. So we essentially want the same thing, but now in the context of our science applications. Right? So the programmer's going to be developing, writing, expressing their software in terms of a generator that when executed will generate the DAG. And then the runtime has responsibility for scheduling, placement, and all of these other good things. Knobs that you can introduce either algorithmically inside the generator or external to the generator in the runtime give a lot of flexibility in giving you portable and tunable performance. There are some challenges there. Writing a generator like this turns out to be not all that intuitive for some people. But certainly, once you've seen how to do it on a few familiar problems, it becomes straightforward. As a quick overview, the TTG basically looks at a high level like a data flow programming model. And so it works fully distributed. A template task is essentially the operation, and then some ID that labels that task. And so if you're iterating, say, through a for loop, it might just be the index on a for loop. If you're iterating through some hash table, it'll be maybe the keys in the hash table. If you're doing a matrix multiply, maybe the index is the triplet of indices that identifies a task in that. So you've expressed now abstractly a data space and an iteration space, and now we can start flowing data by connecting tasks that have inputs that we identify as terminals and outputs that are the output terminals, and you basically connect, right? And so there's a various C++ APIs for composing these things, and fairly extensive use of C++ templates to make this easy. And there are multiple backends to implement this. A key thing is that the runtime manages nearly everything, right? So once you've kicked off computation, it's managing scheduling, it's managing all of the data motion, and it's looking at your C++ lambdas or functions to basically examine the constants, mutability characteristics of all of the inputs and outputs to basically use that information to decide whether it has to copy something or move it between memory spaces and what has to happen in terms of updates. I'm going to actually skip over, actually, part of what makes this work is that we can handle very small tasks, right? With a lot of detailed attention by the team to managing contended atomic operations and things like that. More detailed termination detection algorithms. We've got down to the point where the overhead on a task on a sort of fairly generic x86 CPU is of the order a few hundred nanoseconds. So we can compute at a very fine grain in this manner with all of the dependency analysis and so on. I'll skip over that so that we can finish on time. One of the key focuses over the last couple of years has been on support of hybrid systems. Of course, it's complicated in itself. We can maintain this attribute that the runtime is looking after the data motion, moving data, potentially between multiple GPUs on a single node or between nodes for the application. And that's done through an abstraction called a TTG buffer, which is essentially a memory space which user-defined data structures can wrap. And tasks, of course, are executing primarily on the CPU, and there may be multiple steps needed in a task in order to sensibly execute and execute efficiently an operation on the GPU. And so we have to navigate various points within a task now where something might block, but we don't want it blocking the CPU on the host or consuming an entire thread. So we're actually now using coroutines to implement this, and it's turned out to be very successful. So a single task can go through internally go through multiple cycles of launch kernels, wait for a result, inspect the result, launch another kernel as needed, and then eventually propagate results to successor tasks. And here's what basically the code looks like. This is actually real code that basically doesn't do anything, but is expressing to you the sort of like the complexity of expressing this stuff and having this all automated. So that's actually really where we are now in the project, kind of like state of the art, beginning to get for the very first time multi-resolution code running on the GPU. So it's an exciting development. So there's a link to more information about TTG and some of the publications and so on that sit under that work. And with that, I'll thank you and also, again, the organizers. Thank you.